Hi everyone, I'm John, and I'm here with my colleague Vivek to talk about source separation with deep generative priors. The problem we've addressed in this work is single-channel source separation. What that means is that we want to decompose an observed signal M into a linear combination of source components X. This is a highly underdetermined problem. To see why, let's take a look at this example of a mixture of components. On the right are two possible separations of the mixture. In both the top and the bottom rows, the components x1 and x2 add up perfectly to the given mixture. But from an intuitive perspective, the example in the bottom row is clearly a much better answer. To formalize this intuition leads us to the perspective of Bayesian source separation. In this work, we treat source separation as a sampling problem. We want to sample from the posterior distribution over components given a mixture. The idea is to use modern generative models as priors over components P of X, and this allows us to leverage modern generative modeling research to improve our results. Let's look again at that mixture from the previous slide. For likelihood, we'll use a simple Gaussian distribution. We'll make the variance gamma small to ensure a good reconstruction of the mixture. On the right now, we see three possible separations of M. In the top row, the two components add up to the given mixture, but they have low probability under the prior. They don't look like natural images. In the middle row, the two components have high probability under the prior, but low probability under the Gaussian likelihood. They don't reconstruct the mixture M. In the bottom row, the components are likely under the prior, and the mixture is also likely. By sampling from the posterior distribution, we hope to get separations like the third row, rather than the first or the second rows. Before diving into the details of our algorithm, let's take a brief look at our results. We focus on visual source separation because of the availability of strong generative models for visual datasets. On the left are examples of CFAR10 separations using an NCSN model as a prior. On the right are examples of LSUN separations using GLOW as a prior. For models like GLOW that parameterize the log likelihood, we compute gradients by automatic differentiation with respect to the network's inputs. This is different than the usual automatic differentiation, which differentiates with respect to the parameters. While we focus on these two models for our empirical results, our algorithm can be applied using any generative model so long as we can compute gradients of the model log likelihood. This includes energy-based models like NCSN, invertible models like GLOW, as well as autoregressive models or variational autoencoders. However, our algorithm cannot be applied to GANs because these models do not directly compute probabilities of data points. The rest of this talk is divided into two parts. In the first half, I'll introduce the basis separation algorithm that we use to sample from the posterior distribution over components. In the second half, Vivek will discuss our empirical results and discuss how we can evaluate separations of ambiguous mixtures. The idea of our algorithm, which we call basis separation, is to sample from the posterior using Langevin dynamics. If you're not familiar with Langevin dynamics, it's an iterative procedure that looks a lot like gradient descent, with the addition of a noise term epsilon in each gradient update. Under certain conditions, the iterates x sub t converge to a sample from the posterior distribution. In practice, mixing is far too slow. The problem is that the likelihood surface is highly non-smooth and non-convex, which is illustrated by the cartoon distribution on the right. We accelerate Langevin dynamics using a form of graduated optimization, which we adapt from the recent paper by Song and Ehrman. The idea is twofold. First, smooth out the distribution by convolving it with a high bandwidth Gaussian. The smooth distribution is easy to optimize, but the optimal solution is wrong. Next, we run gradient descent on the smooth surface while simultaneously decreasing the bandwidth of the Gaussian convolution. As the bandwidth approaches zero, the smooth distribution approximates the true distribution. Over time, we gradually decrease the learning rate to prevent the optimization from blowing up as the surface becomes less smooth. Before moving on, note that Langevin dynamics allows us to avoid computing the partition function P of M because the gradients of this function with respect to x simply vanish. There are a few details when it comes to actually implementing this noise annealed Langevin dynamics. First, how do we compute the likelihood under the smooth prior? We do this by fine-tuning several versions of a pre-trained model using data corrupted with different levels of additive Gaussian noise. We find that this training process converges quite quickly in just a few epochs. Another problem is that Langevin dynamics only converges as the learning rate eta, the smoothing sigma, and the reconstruction penalty gamma go to 0. So we're going to need to introduce an annealing schedule that sends eta, sigma, and gamma to 0 simultaneously while t goes to infinity. We propose a triple annealing schedule for conditional sampling that extends the double annealing schedule previously introduced by Song and Ehrman. The idea is to balance the 3 update terms in the Langevin dynamics. Under certain assumptions about the prior distribution, we show in the paper that the norm of the first term is proportional to eta squared over sigma squared. The second term is just the gradient of a Gaussian likelihood with variance gamma, which has norm eta squared over sigma squared. Eta squared over gamma squared. And the Langevin noise has unit variance, so the norm of the third term is just eta in expectation. This motivates us to set gamma squared equals sigma squared, and decay eta proportional to these quantities as t goes to infinity. We send all 3 hyperparameters towards 0 at an exponential rate. This means that the final smoothed prior is a very close approximation to the given prior distribution, and reconstruction of the mixture is enforced to epsilon accuracy. And with that, I'm going to turn things over to Vivek to talk about the empirical results. Thank you.
Thank you, John. So my name is Vivek, and in the rest of this talk, we'll dive into some of the results produced by our algorithm. We'll also discuss a bit about the qualitative and qualitative metrics. In addition, I'll describe the non-identifiability problem in source separation and how we can tackle this in our evaluations. In this first example here, you can see the source separation of a mixture of 2 CFAR10 images which have been added together. This mixture is shown here on the left side, and our algorithm separates out the components shown here in the middle. The originals that were used to create the mixture are shown on the right-hand side. Notice that our algorithm does a very good job of separating out the mixture, even in very challenging components such as these, the horse and the dog, which is enlarged, where they're both the same shade of white, and it's very hard to discern them in the original mixture. In this next example here, we show mixtures consisting of 4 MNIST digits which have been summed together. The 4 digits are shown on the left-hand side, the originals, and the mixture is shown here in the middle. Notice that the mixture, it's very hard to discern the different digits. In fact, you can take a look for yourself and try to see if you can pick out some of the original images in the mixture, and it's a very hard task. But our algorithm is able to do a pretty good job of separating out the original images that were used to construct the mixture. In this example, we show a video of the sampling procedure taking place. Notice that we start with a noisy input. This corresponds to the noise temperature sigma. And as we decrease sigma, 2 things happen. First, the reconstruction, or the reconstructed mixture, closely matches the input mixture. And also, the separated components are very high quality components. These are the 2 criteria which we're really trying to optimize for. In this example, we show a slightly higher resolution example on a data set called LSUN, where we have a mixture consisting of 1 church image and 1 bedroom image, and our algorithm is separating them out. In this case, we're using a generative model called GLOW, and we trained a separate model as a prior for the churches and a separate model for the bedrooms. This works slightly better than training the same generative model as a prior for both types of source components. When trying to evaluate our source separation, one key observation is that in many cases, source separation is an ambiguous task, and comparisons with the ground truth are not always meaningful. So take a look at this example here, where the separated and the original are very different in terms of color, but they both look quite reasonable in terms of reconstructions of the original. And in this second example here, we see some structural ambiguities. So in the first case, the part of the leaf of the frog becomes a mountain behind the horse. And in the second case, the red car in the original has a kind of border, and this border gets applied to the airplane when the algorithm runs the separation. In fact, looking at that specific example, it's impossible to tell whether the car or the airplane should have the border around it. In all these cases, both the separation and the original sum together perfectly to the original mixture, showing that there are ambiguous and different ways of separating out this mixture. In fact, when we rerun the algorithm many times, we find that we get slightly different results every single time. This really supports the idea that we are in fact sampling from the posterior distribution. And this posterior distribution doesn't always have a single peak. In fact, it might have high probability regions in many different areas. In some cases like MNIST, where the original components are uniquely identifiable in the mixture, we can use a metric like peak signal to noise ratio to compare with the ground truth. However, in other cases like CFAR10, where there are ambiguous and different ways to separate out a mixture, we can't use such comparisons that rely on the ground truth. Instead, we choose to use metrics like inception score and FID. These are widely used in the generative modeling community and are a measure of how good a source is, which is really what we are trying to solve here. We are trying to create two sources which sum to the mixture and which are high quality sources, even if they are not exactly the same as the ground truth. So here we show quantitative results on MNIST, where in this first case, we're using peak signal to noise ratio, and we point out that we outperform several baselines which we've used as comparison. One interesting observation is that when you look at GLOW provides an explicit likelihood estimate when you run a single sample, which means that we can actually rerun the algorithm multiple times and use the output from GLOW as an estimate of how good the separation is. So this allows us to run it multiple times and use the best output according to the model. This is denoted by GLOW 10x in the table, and it outperforms a single optimization of the GLOW model. So this shows that in some cases, models which provide an explicit estimate of the likelihood, like GLOW, can be more advantageous than models like NCSN, which only provide an estimate of the gradient of the likelihood distribution. In this second case, we're showing inception and FID scores for CFAR10. Again, you can see that we outperform several baselines. For more details on these experiments, you can feel free to check out our paper. Another interesting application of our work is that we can tackle the image colorization problem using source separation. Image colorization is the problem of taking a grayscale input and colorizing it in a realistic way. This has many applications in a wide variety of scenarios like cinematography and photography. Notice that, in fact, a grayscale image can be considered as a mixture of the source components. So source separation can be seen as trying to separate out these different colored inputs from the grayscale image. And the results here show that, in fact, our algorithm does a pretty good job of separating out the different color channels to create a colorized input, and is in fact very close to the original ground truth images in terms of how realistic they are under inception and FID score. And further, in this case, it's easy to see that the original color images which were used to create the grayscale are in fact not uniquely identifiable at all. For example, looking at, the car in the middle, it could be green or blue or red because all these different hues have the exact same grayscale value. So this supports the idea that, in fact, the ground truth components are not always uniquely identifiable in source separation problems, and that comparisons with the ground truth do not always provide a meaningful evaluation result. And finally, we'd like to thank the different organizations that have helped us out on our journey. This includes the UW Paul Allen School of Computer Science and Engineering, as well as the Washington AI Lab, the UW Reality Lab, and the National Science Foundation. In addition, you can check out the GitHub link with all the code in this link that we've presented here. Thank you.